There's a formula made from 4 ordinary materials you can buy at any hardware store for under $15. It produces a finished surface so refined, so porcelain smooth, so structurally superior that luxury kitchen brands sell the exact same result for $800 and call it an artisan piece. The concrete industry has known this for over a century. Not a product, not a brand, not a proprietary compound locked behind a patent. Sand, cement, chopped fiberglass, epoxy resin. 4 materials sitting in plain sight at every hardware store in the country, priced at a combined $15. The fabricated stone industry generates over $28 billion a year in the United States alone. Composite sinks, designer concrete basins, cast polymer tubs, all of them trace their chemistry back to the same combination. They did not invent a new material. They hired a marketing team and built a wall of pricing between you and the formula. That wall ends today. Welcome to Fixvival. If this knowledge matters to you, the subscribe button and the bell are the best way to make sure it survives. Here we open the vaults. Now let me take you back to where this all begins. The year is 1849. A Scottish engineer named William Wilkinson files the first patent for reinforced concrete, a structural system that embeds tensile material inside compressive stone. He created something neither component could achieve alone. But Wilkinson did not invent the idea. He formalized it. Builders had known for centuries that stone alone cracks under tension, and that fiber embedded within a matrix changes everything. In ancient Mesopotamia, craftsmen mixed chopped reed fibers into mud bricks to prevent shrinkage cracks. The same instinct drove Roman engineers to press horsehair into plaster mortar. In 18th century France, boat builders layered textile fabric inside cement hulls. Every civilization that worked with brittle materials eventually arrived at the same conclusion. Fiber changes the failure mode. Instead of a catastrophic single crack, a fiber-reinforced matrix distributes stress across thousands of microscopic threads. The piece does not shatter, it holds. That single insight is the foundational principle behind every composite material in modern engineering, from aircraft fuselages to Formula One chassis. Fiberglass specifically enters the story in 1938, when Owens Corning begins commercial production of glass fiber strands for industrial use. By the 1950s, the boat-building industry adopts fiberglass-reinforced polyester resin, producing hulls lighter and stronger than wood or steel at a fraction of the cost. But here is what the composites industry never wanted the general public to understand. The same fiber reinforcement technology can be applied to something as simple as a kitchen sink, using cement as the matrix instead of polyester resin, at a material cost that makes the entire premium fabricated stone market look like an elaborate confidence trick. Let me explain exactly why this formula works, because the science is elegant, and the fabricated stone industry would prefer you never understood it. Standard concrete has a fundamental weakness. It is strong in compression. It resists being crushed, but weak in tension. It resists being pulled apart. Apply a sideways load or an impact to an unreinforced concrete piece and it cracks. Because the calcium silicate crystal structure that gives concrete its hardness has almost no capacity to flex before fracturing. Chopped fiberglass changes this at the microscopic level. Each strand of glass fiber has a tensile strength of approximately 300-400 megapascals, stronger than structural steel by weight. When thousands of these strands are distributed randomly throughout a cement matrix, they create a crack bridging network. When a stress fracture begins to propagate through the cement, it immediately encounters glass fibers crossing its path. Those fibers must be pulled out or broken before the crack can advance. The energy required to defeat those fibers gives fiber-reinforced concrete its resilience. The plasticizing additive performs a different but equally important function. Cement mixed with water alone produces a material full of microscopic voids, air pockets and water channels that reduce strength and create surface porosity. A plasticizer works by reducing the surface tension of water molecules, allowing the cement slurry to flow more completely around every aggregate particle. Less water means fewer voids. Fewer voids means higher density. Higher density means greater compressive strength and a more finished surface. The epoxy resin top coat introduces a third layer of chemistry. Epoxy is a thermosetting polymer. It begins as a liquid and permanently crosslinks into a rigid, chemically inert solid through a catalytic reaction between resin and hardener. Once cured, epoxy bonds to prepared surfaces at the molecular level is impervious to water and resists most household chemicals, and produces a surface hardness close to glass. Applied over a sealed, sanded concrete substrate, epoxy does not merely coat the surface. It becomes a second structural skin, flexible enough to accommodate minor thermal expansion, hard enough to resist abrasion, and chemically bonded tightly enough that delamination under normal use is essentially impossible. The combination of fiber reinforcement, plasticized cement matrix, and polymer surface treatment produces a composite whose mechanical properties exceed industrially cast products, at approximately 2% of the retail price. Now here's where the story takes a turn that should make you genuinely uncomfortable. The fabricated stone and engineered stone surface industry did not emerge because hand-cast concrete was inadequate. It emerged because hand-cast concrete could not be monetized at scale. A product that a single person can make in a garage with $15 of materials is not a product opportunity. It is a problem to be managed. The managed solution was proprietary complexity. By the 1980s, countertop and sink manufacturers began filing patents not on the underlying materials. Cement, fiber, and resin cannot be patented. They are commodities, but on specific production processes, surface textures, and colorant formulations. They built brands around the mystique of industrial fabrication: precision cast, engineered stone, polymer-modified composite. Language designed to suggest that the process required equipment and knowledge beyond the reach of any individual. The 1978 trade dress regulations made concealment even easier. Manufacturers could describe products using proprietary material names rather than standard chemical terminology. A cement fiberglass composite with an epoxy topcoat became a mineral polymer matrix surface, or an engineered cast resin composite. The same chemistry, buried under vocabulary that made it unrecognizable. Retail pricing completed the illusion. A fiberglass reinforced concrete sink produced in a factory arrives at the consumer with $600 to $800 of margin attached. The material cost at the factory is rarely above $20. The labor cost in automated facilities is minimal. What you are paying for is the brand and the carefully constructed belief that this object could not be made any other way. And here is the detail that makes the economics most clear. The premium fabricated stone market depends on replacement cycles. Sinks get scratched, surfaces get stained. The perception that a damaged surface must be professionally refinished drives a service economy. A person who understands the formula can refinish a damaged epoxy surface with a $30 resupply kit in an afternoon. The industry does not want that person to exist. The knowledge never disappeared. It moved underground into the communities the industry cannot reach. The precast concrete fabrication community, artisan makers producing countertops, sinks, and furniture, has grown steadily since the early 2000s. This growth happened largely through direct knowledge, sharing outside mainstream media channels. Craftsmen regularly produce pieces structurally and aesthetically indistinguishable from premium commercial products at material costs between $5 and $25, depending on size and finish complexity. A 2019 structural study measured the mechanical performance of hand-mixed glass fiber reinforced concrete against commercially produced GFRC panels. Hand-mixed specimens, using standard chopped E-glass fiber at a 3% ratio, achieved flexural strength within 8% of commercial products. The industrial advantage of vibration table compaction can be substantially closed with manual tamping and extended wet curing. Epoxy research confirmed that concrete substrates sealed with acrylic filler showed adhesion values exceeding factory-applied coatings. The surface preparation sequence, mechanical abrasion, sealing, and graduated sanding, is the variable that determines coating longevity. A maker in Vermont documented building 47 concrete sinks using this method and installing them in residential homes. After 3 years of daily use, none showed structural cracking or failure beyond minor surface scuffs on 3 pieces. He refinished those in an afternoon. His total material cost across 47 pieces averaged only $19 each. Here is exactly what to do. And it is almost insultingly straightforward once you understand what each step actually accomplishes. Materials required. Total cost: under $15. Fine sifted sand, Portland cement, chopped fiberglass, plasticizing additive, acrylic filler, epoxy resin, pigments, molds, and cooking oil. Step 1. Dry mix. Build the fiber network. Combine sand, cement, and chopped fiberglass in a large container and mix thoroughly while completely dry. Fiberglass distributes more uniformly in dry conditions, creating the crack-bridging fiber network before any moisture compromises strand separation. Consistency of movement matters more than speed. Step 2. Plasticizer preparation. Dilute 50 ml of plasticizing additive into your mix water before combining with the dry materials. Never skip this step. Pre-diluted, it disperses completely through the slurry and eliminates the microvoids that compromise surface finish and structural density. Step 3. Mold release. Apply a thin, even coat of cooking oil to every interior surface of your mold before placing any material. This prevents concrete bonding to the mold during curing and eliminates demolding fractures. An uncoated mold can destroy a piece that took 24 hours to cure. Step 4. Casting and compaction. Fill the mold in layers, tapping the exterior firmly after each addition to expel every air pocket. Repetitive tapping is the difference between a piece that looks handmade and one that looks fabricated. Allow minimum 24 hours initial cure before demolding. Step 5. Wet cure. After demolding, submerge the piece completely in water for 24 hours. This process maintains the moisture required for continued cement hydration. A wet-cured piece achieves 20 to 30% higher compressive strength. After the water bath, rest the piece for 48 hours. Step 6. Acrylic sealing. Apply 3 coats of acrylic filler to all surfaces. This creates a chemically compatible bonding surface for epoxy. Sand between coats with 320 grit. Finish with 400 grit. Remove all dust with a damp cloth to ensure a perfect finish. Step 7. Epoxy application. Measure component A and B at a 70-30 ratio. Mix for 20 minutes with slow, deliberate strokes. Add pearl white pigment. 1 drop is sufficient to shift the resin from transparent to porcelain. Mix for another 20 minutes. Apply with a soft varnish brush in continuous strokes following the shape of the piece. A single properly applied coat is sufficient. Step 8. Edge detail. Using pigmented resin shifted to gray, apply controlled drops along the upper edge. Allow gravity to draw the resin naturally. No 2 pieces will ever be identical. This is the precise characteristic that high-end artisan studios charge a premium to replicate. Step 9. Final cure. Do not touch or use the piece for 7 full days. Epoxy achieves full strength over approximately 168 hours. After 7 days, rigid, waterproof, non-porous, professional. Total investment, under $15 in materials, and 90 minutes of active work. The rest is waiting. A design studio sells a near identical basin for $740. Their material cost is under $20. The gap is not craftsmanship. It is a story you believed about what you were capable of making yourself. The chemistry has not changed in 4,000 years. What changed was the story told around it. The story was never about the material. It was about keeping you on the purchasing side of the transaction.